Okay, before we begin, I'm going to give a shout out to Maddie Block. Love you, Maddie. And let's get going. This is where we left off yesterday. I'm going to warn you, I'm going to talk pretty fast since this is a flipped lesson because you have the pause button. So if I'm going too fast or you don't understand something, of course, pause it or rewind and rewatch it again. So with that being said, let's go. We're going to use this equation in the very next problem. So here we go. We have two problems and we want to know what delta S is. And so I just told you we're going to use this formula, delta S equals negative delta H over T. So we're going to label this problem number 1. So let's go. So delta S is going to be equal to negative 125 from the problem over T, which is going to be 298 Kelvin. For entropy, you must use Kelvin for your temperatures because the units are joules per Kelvin. So per mole Kelvin. And so then let's calculate that, and we get that it is equal to a positive 0.419 kilojoules per mole K. And so because I know that joules are the normal answer, I'm going to go ahead and remind you that there are 1,000 joules in a kilojoule. So we're going to convert that, and we're going to end up getting a positive 419 joules per mole K. Now let's do the same thing for reaction number 2. So same process. We're going to have delta S equal to negative 778 over 298. So that's going to give us negative 2.61. Converting it to joules times 1,000. It's going to be a negative 2610 joules per mole K. All right, that should be easy enough. Let's move on to Gibbs free energy. Okay, Gibbs free energy is basically a measure of the thermodynamic favorability. Ultimately, that is what is going to decide if something is thermodynamically favored, taking into account both the enthalpy and the entropy. We want a negative delta G. A negative delta G is going to tell us that we are spontaneously favored, not spontaneous, we don't use that word anymore, thermodynamically favored. At equilibrium, this is going to be important later on. This is an example of when ice is melting at the equilibrium point. Delta G is going to be 0, and that is going to be important for us. Okay. All right. So Gibbs free energy can be calculated in a variety of ways. 2 ways are basically just like what we've been doing with enthalpy, where we can do the summation equation, or Hess's law, where we rearrange our steps in our equation and then the overall is added together, and then some fun new ways, which we did today in class with the worksheet, with the delta G is equal to delta H minus T delta S. Also, we're going to use the equilibrium constant, the reaction quotient, and there's even a new way that we will learn about in electrochem, which is using Faraday's constant and energy. Here's the first way. That should look really familiar by now. Same thing for enthalpy. The Gibbs free energy for formation of a free element in its standard state is 0. We already did this one in class. So remember reminding you that since entropy is in joules per mole K, we have to convert that to kilojoules because delta H is kilojoules and Gibbs free energy is generally given in kilojoules as well. Here's one that if we are not at standard state, how could we get what delta G is? Notice that the naught thing has disappeared, and so we would find out what delta G naught is, what it normally is under standard conditions, and then we'd use the RT natural log of Q, Q being the reaction quotient, products over reactants raised to their coefficients. But here's something new, and that is we got to use a different R value. Okay, because we're dealing with energy, we want that joules in there, so we're going to use 8.3145. Here's the problem. If I look at this equation, normally that's in kilojoules, right? And then that's in joules. So you guessed it, we're going to have to convert one or the other. I do not care if you convert the Gibbs to joules or the R to kilojoules. It doesn't matter to me. You just pick one and stick with it. Just pick one and stick with it and be consistent so you don't accidentally convert one and the other one when you didn't need to. Also, calculating delta G, if I am at equilibrium, is the negative RT natural log of K. lovingly called the Ratlink equation, and then K, of course, is your equilibrium constant. And then this one will show up in electrochem. It's got some new constants in there, Faraday constant and E cell for an electrochemical cell. We're not going to even really talk about it right now. We're just going to wait till we get to electrochemistry, which is our next and last unit before we start our review. All right, you should probably memorize this next part. We kind of talked about it with the worksheet. I actually like the chart that's coming up better, but I wanted to make sure I wrote this as thermodynamically favored or not favored instead of spontaneous. But most of the charts that are out there that I can grab a picture of off the internet have spontaneous, so I wanted to say thermodynamically favored. But here we have it. You can look through that. We already did that in class, so that kind of helps you, but that's a good thing to just memorize. All right, now let's work some problem with all the different ways that we can calculate Gibbs free energy. Okay? Here we have a problem, reaction of water and oxygen making hydrogen peroxide. They're giving us the delta G values, so that means this is a summation equation because they gave us the values. So we're going to take delta G is going to be equal to products minus reactants. So we're going to have 2 times negative 27.2, and we're going to subtract from that 2 for the liquid water. If you were looking these up in a chart, make sure you look up liquid water, not gaseous water. And then, of course, that's it because oxygen is 0. They don't even give it to us. So then our delta G value is going to be equal to 59 kilocalories because that's what they gave us per mole of reaction. Okay? That is going to be not thermodynamically favored. I'm going to abbreviate because I'm running out of room. Because it's a positive value, it actually wouldn't be favored. Okay? So there's the one way. I'll try to give you an example of each one. Next way is calculate, this is going to be a long one. Calculate delta H, delta S, and delta G. So ultimately, we're going to need this equation at the end. Delta G is equal to delta H minus T delta S. But before we can do that, we're going to have to calculate those two. So delta H is going to be 2 times negative 390. Okay, that's supposed to be, it's 396. I just realized when I typed this in on that, it's 396. Because I'm looking at my math going, what happened there? Okay, so, and that's going to be minus 2 minus 297. And of course, 0 for oxygen. So that's going to be a negative 198 kilojoules per mole of reaction. Now let's calculate delta S. So we're going to have 2 times 257 minus 2 times 248 plus 205. And then that is going to end up being a negative 187 joules per K mole or mole K, whatever. Now, here's what I like to do because I don't want to accidentally put in, because this is a very common mistake, I do not accidentally want to list my entropy in this equation right here as joules and screw up and not realize that I screwed up. So I'm going to immediately convert that to kilojoules. So I'm going to immediately say that's negative 0.187 kilojoules, so that, and all the rest of it, blah, 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 moles per K. So now, let's put it in. Delta G is going to be negative 198 minus 298 times a negative 0.187. And then that ultimately ends up being a negative 142 kilojoules per mole reaction. It doesn't ask us if it's favored, but I like us to go ahead and list that it is so that we're paying attention to that. So it's because it's negative, it would be thermodynamically favored. We're going to abbreviate that. On the AP exam, do not abbreviate. Okay? All right. Pretty straightforward. Let's go on to the next problem, which is going to be our Hess's law type equation, because I've been given two pathways for diamond to go to graphite. Okay, and so I quickly see that, guess what, I'm going to have to reverse this one. Okay, I don't need to do any coefficients, so it's just going to be this one reversed. So we're going to reverse that one. And so to save time, I'm just going to jot it up above, reversed. So I'm going to have CO2 going to carbon graphite, abbreviate that, plus O2. Crossing out O2, O2, CO2, CO2, so that I am left with this one down here, and then I have this is a plus 394, so my overall delta G is a negative 3 kilojoules per mole of reaction. So it is in fact thermodynamically favored. However, kinetically, it is so very slow that it seemingly doesn't happen. Because remember, kinetics is rate, thermodynamics is it favored, aka spontaneous. We just don't use that word anymore. Okay. Moving on, next problem. Oh, this one's a fun one. Okay. So we have this reaction. We've got some delta H values and some delta S, and it says calculate the equilibrium constant. What? So we're going to use this equation. Delta G is equal to negative rat link. All right, problem is we don't have delta G, do we? No, we do not. But we can get delta G, can we not? By doing delta H minus T delta S. And since the only things we have available to us are H and S, then we're going to have to calculate those as well. Okay, so delta H, products minus reactants. So I've got 2 times a negative 826 minus, well, 0, because they're both elements. So that's going to be a negative 1652 kilojoules per mole. Now let's do some delta S, which is going to be 2 times 90 minus 4 times 27 plus 3 times 205 equals a negative 543 joules per mole K. Immediately take that to negative 0.543 so that we don't plug it in wrong. So then that's going to take me to delta G is going to be a negative 652 minus 298 times a negative 0.543, and that ends up giving me negative 1490 and some change, but we're just going to go with that. And that is kilojoules per mole. All right. That means I'm going to need this equation now and this number. And I'm going to clear the screen because clearly I have no more room. So here we go, erasing all that. So I'm going to rewrite what we're going to be using. Delta G equals negative rat link. And that we found our delta G to be negative 1490 kilojoules per mole. All right, we know R is in joules, and we've got a kilojoules for our delta G. Your choice here. I think it's just easier to convert the R. I just do. I don't know why. Because I can do that. I don't know why. Pick one and stick with it. So that means when I'm going to plug this in, I'm going to have a negative 1490 equals a negative, and I'm going to say 0.0083145 kilojoules per mole K times 298 is natural log of K. So when I do that math, I get 601, and it's negative, which is equal to natural log of K. It's not negative because it's a negative and a negative. Sorry about that. My bad. Knew something didn't look right. And then if I'm going to do E raised to the 601. So try throwing that in your calculator, and guess what you get? Overflow. At least that's what I get on my calculator. Okay? So what that means is it's a really big number, like so big that your calculator won't hold it. So if it's a really large K, what does that mean? That means that it is very much product favored, which if you look back at this is the rusting of iron by oxygen. We know that to be thermodynamically favored, don't we? Because it happens all the time. If you ever got a number like this on an AP exam, A, I'd be surprised. But B, if you did, don't panic. Okay? All right. Only got a couple more left, and then we're done. Continuing forth. This one is the methanol, synthesizing of the methanol. It says calculate delta G at this reaction where we have 5 atmospheres and 3 atmospheres. So because I don't have 1 atmosphere of my gases, these are not standard conditions, so this means I am not at equilibrium. Also the fact that delta G doesn't have a naught on it, and so we're going to be using this equation, delta G is equal to delta G naught, put the naught in the wrong spot, plus RT natural log of Q. Okay? So there's going to be some numbers that I need to give you so that you don't have to pull them up. So I'm going to give you that. Of course, this is going to be 0 for delta G naught because it's an element. This is a negative 166.6, and then this one is a negative 137. Okay? Probably has some change with it, but I forgot to write it down, so we're going to go with negative 137. Okay? So we need to, first of all, calculate the delta G for this reaction. Okay? So delta G naught is going to be a negative 166.6 minus a negative 137, products minus reactants, and I get a negative 29, negative 166.6 minus negative 137. I get 29.6, negative 29.6 kilojoules per mole. So now I can plug it in up here. Okay. Before I go further, let's go ahead and get Q. Products over reactants, raised to their coefficients. We do not include liquids, so 1 on top. And then hydrogen is 5. So because of that 2, we're going to square it. And then 3. So we end up getting 1 over 75 when we do that. 1 over 75, which is 0.0133, lots of repeating 3's. So now we plug everything in. So delta G equal to negative 29.6 plus our R value. I'm going to take it to kilojoules because that's what I'm already in, times 298 times the natural log of 0.0133. Depending on how you plug that in your calculator, where you rounded, where you didn't, if you plugged it in all at once, however you did that, you might get slightly various numbers. But what I get when I'm all said and done with my rounding is a negative 39.7 kilojoules per mole. And that would be thermofavored, right? Okay? All right, that's fun. That brings us to exercise 10, which I believe might be the last thing. And then there's some stuff on there that I didn't put in the last slide because you know how to read. All right, so let's do this one. Okay? This says find the thermodynamic boiling point of H2O gas to a liquid. And then it gave us our heat of vaporization and our entropy of vaporization. Okay? Both of them being positive numbers. So before I do anything, I don't even know what I have to do yet, but before I do anything, I know that I'm going to have this as a kilojoule so that I don't mess it up. So that's just my habit when I'm doing this sort of thing, is just go ahead and put it in here. And it is mole K. I forgot that when I was typing it. Okay? So I'm at the thermodynamic boiling point. Okay? The boiling point of any item, if I'm at the boiling point, means I'm also at equilibrium. And earlier in the slideshow, I said at equilibrium, delta G is equal to 0. Okay? So if I take this equation and I set this equal to 0 is equal to minus H, not minus H, delta H minus T delta S, then I can rearrange that equation and get that thermodynamic temperature, or the equilibrium temperature, is going to be equal to T is equal to delta H over delta S. Okay? That is an important concept. This is something that you need to, I don't know if you really need to memorize it, but a lot of times kids get to a test and they get confused or whatever. So if they would just memorize that at equilibrium, T is equal to delta H over delta S. So then it's going to be 44 kilojoules per mole divided by 0.1188 kilojoules per mole K. So then my final answer is 370 K. Okay, which is going to be slightly different if we, if you actually work that out, it's going to be 97 Celsius, which is a little off, but these are the numbers we were given, so we would go with the numbers we were given. Okay, and that's how you do that. And I think that is the end. Got that one last section in your notes, just some little extra information, and we are done. Look at that. That was a lot of work in 23 minutes.